In this lecture, we're going to accomplish a few things. First of all, we're going to use the product rule in this discussion, but also we're going to go back and look at a little bit more closely at how you can use calculus to determine what the shape of a graph is, even if you don't know what all of the constants are. So we're also going to look at parameters. So recall that a parameter is something that's like a variable, except it's an unknown constant. So for the purpose of performing the actual problem, you treat parameters as constants. They're not actually variables, even though they have a letter or some sort of variable name assigned to them. So the family of functions that we're going to look at today is the family, let's do P of t. So P of t is equal to a t e to the minus bt. Yeah, that's good. So functions like this, of this form, so basically a and b are positive parameters. So we treat a and b as constants. We just don't know what those constants are. So for a different choice of positive numbers a and b, you get a different actual function. Although all of these functions satisfy this basic form, so that's why we call it a family of functions. So this is a family of functions. So we want to study this entire family of functions at once. So we want to know something about what these functions look like without having to commit to a particular value of a and b. And we'll use calculus to do that. If we actually knew the values of a and b, we can just graph it, and then that would be the end of it. However, we want to be as flexible and as general as possible, so we want to say something about all of the members of this family of functions. So functions like this can be used, for example, to model power surges. You'll see why when we come up with a graph of this function, you'll see why that's true. So in order to do this, we're going to have to rely on all of our basic information about the behavior of a function and what's happening with its derivatives. So we've talked about this previously in chapter 2, so we're going to go back and actually use some of that theory to figure out what this function actually looks like. So recall we have a graph. If you have just a function f, f prime, f double prime, and a bunch can be said so about both the trend and the concavity. Trend is just my word for whether it's increasing or decreasing. So this chart's really divided into two separate sections, because a function can be increasing, concave up, increasing, concave down, decreasing, concave up, decreasing, concave down. So these two options and these two options are basically taken separately. You're either in this column or column 1 or column 2, and you're either in column 3 or column 4. So you get basically 4 possibilities. So if f is increasing, we know that the derivative is positive, and there's no information about the second derivative. If the function's decreasing, we've seen that the derivative is negative, and there's no information about the second derivative. So knowing only that the function's increasing tells us that the derivative is positive. Conversely, whenever the derivative is positive, we know that the function must be increasing. So we can already use this to gain a good feeling on what the graph of P of t is going to look like. But we can also use information from the second derivative. So concavity, concave up, concave down. If a function is concave up, that means its derivative is increasing, which means the second derivative must be positive, because after all, the second derivative is just the derivative of the derivative. So the derivative is a function that's increasing, so its derivative must be positive because of this, right? It's the same. And then similarly, if a function's concave down, the derivative is decreasing. That's not decreasing. The derivative is decreasing, and the second derivative is negative. So that's the handy chart that basically tells us everything we can say about the sign of the derivative, the sign of the second derivative, and then whether or not the function's increasing, decreasing, concave up, or concave down. Okay, so we're going to use this information to figure out the shape of the graph. And I'm going to make some room here. So in order to do this, we're going to need to look at the first derivative and the second derivative of the function p of t. So first of all, to find the derivative, p prime of t, we're going to need to use the chain rule, or the product rule, because we basically have a product of two functions. So our first function is t, and our second function is e to the b minus bt. And then the a out front is just a constant which stays along for the ride. So the derivative is going to be given by, so it's the first function, so a stays along, so it's the first function, which is t, times the derivative of e to the minus bt. Now, since this is an exponential function, we rewrite it, e to the minus bt, and then we multiply by the derivative of the exponent, which is negative b. So I'm going to make some space there. So when we multiply by the negative b, I'm going to put the negative b up front. So this is the first function right here times the derivative of the second, and the derivative of the second is negative b e to the minus bt. So then I'm going to add to that the second function, e to the minus bt, times the derivative of the first function. In fact, why not? Let's just say the first function is at. So the derivative of the first function, the derivative of at, is just a, since a is a constant. So there is the derivative of the first function. So this is f prime times the second function. And this is the first function times the derivative of the second, including this stuff over here. So first function times the derivative of the second plus the second function times the derivative of the first. Now I'm going to rewrite this. I'm going to change the order of these two terms, because since this one starts with a minus sign, it's better to say a minus b than to say negative b plus a. It's just a little bit, stylistically, it's a little neater. And when you get good, you'll see that coming in advance, and you'll just write them in the reverse order. So when I look at this, I'd say, okay, derivative of t is 1, so we get a e to the minus bt. Derivative of e to the minus bt, the minus b comes down, so it's minus b times, or a b t, e to the minus bt. So that is the derivative of p prime of t. And oftentimes it's useful to factor out any common factors with these problems, because that will let you spot when the sign of something changes more readily. So the common factor here is a and e to the minus bt. So p prime of t is the same as a e to the minus bt times the quantity 1 minus bt. Well, that makes life easier, because this first factor is always positive. A is a positive parameter, and remember, the exponential of any number is always going to return a positive, right? Because the graph of e to the x looks like this. Right, so for any real value x, the return of e to the x is some positive number. So this is positive, and now, so basically the sign of this simple function 1 minus bt dictates the sign of p prime of t, and that in turn dictates whether or not p of t is increasing or decreasing. So let's look at 1 minus bt. 1 minus bt less than 0. Now we can solve this inequality for t to find out at what times p prime is negative. So this is the same as 1 less than bt, And since b is a positive parameter, I can divide by it. So t greater than 1 over b. So p prime is negative whenever t is greater than 1 over b. Now this is a linear function, so it's going to be either positive or negative. So it's safe to assume that the following. So the derivative p prime is greater than 0 when t is less than 1 over b, and p prime is less than 0 when t is greater than 1 over b. So that means that so the parameter b is starting to have physical significance, because the reciprocal of this parameter b dictates at what time the function will go from increasing to decreasing. So when time is less than 1 over b, the derivative is positive, which means the function is increasing. And when the time is greater than 1 over b, the derivative is negative, which means the function is decreasing. So basically, we already have at time 1 over b, the function is going up and then it's going down. So it reaches some sort of maximum at the point 1 over b, right? Because it's increasing up until 1 over b, and then it's decreasing after 1 over b. So at 1 over b, that's going to be the maximum point. And we'll look at maximum and minimum, maxima and minima of functions in more detail in section 4.1. However, right now I just want to get used to it, because really 4.1 is just applying things that we already know. So by applying some of this stuff earlier, you get used to it a couple of times before we actually go through all of the technical details of that. So that's great. We already have a little bit of understanding. It increases and then it decreases. So it's increasing for time less than 1 over b, and then it's decreasing after that. So p is going to be greatest at the time 1 over b. Now let's see if we can gander anything about concavity from the second derivative. So the second derivative, let's use this, right? So here's p prime. So p double prime, remember this. Let's get rid of that. So p double prime, might be a little bit lengthier, so let's save as much room as possible. So p double prime, let's do a different color. Okay, so I can use this factored form for the derivative. So first times the derivative of the second plus the second times the derivative of the first. Now the derivative of this is going to be negative b. The derivative of this is going to have a minus sign too. Okay, let's first times the derivative of the second. Okay, the derivative of the second is just negative b. So negative b. So that's the derivative of the second one. And then times the first, so just a e to the minus bt. So that's the derivative of the second times the first. And then plus, or the other way around, the first times the derivative of the second, plus the second function, 1 minus bt, times the derivative of the first. Now the derivative of the first, we rewrite it, a e to the minus bt, because it's an exponential function. And then we multiply by the derivative of the exponent. So we multiply by negative b. So I'm going to change this plus to a minus to accommodate negative of the negative b. And then this a is going to become a times b. Okay, so we can factor out of this a negative b e to the minus bt, and then we get a minus. Okay, so what did we factor out? I factored out this, factored out that, factored out the minus, factored out the b and the e to the minus bt. So what is left is going to be a times this. So plus, because we factored out the minus. So a times 1 is a, and then a times negative bt is minus abt. So the second derivative is equivalent to minus b e to the minus bt times 2a I could have factored out an a too, couldn't I? Yes, I can. I'll do that in a moment. So 2a minus abt. So in other words, it's equal to minus ab e to the minus bt times 2 minus bt. So there's the second derivative. It's negative ab e to the minus bt times the quantity 2 minus bt. So let's see. Yeah, I think that looks right. Okay. So this part's positive, but then there's a minus sign, so this coefficient's always going to be negative. So that's going to have the effect of reversing the sign of this function 2 minus bt. Okay, so in fact, let's just, now that we have p double prime derived, let's just move it all up to the top. So p double prime is minus ab e to the minus bt times the quantity 2 minus bt. Okay, so let's look at 2 minus bt. So this is similar to right here, except the 0 point is easy to find because if you just set 1 minus bt to 0, you divide by b and you get t is equal to 1 over b. Similarly, this becomes 0 when t is equal to 2 over b. And this function has a negative slope, so it's a decreasing linear function. So it's going to be positive and then negative, and the transfer happens when t is equal to 2 over b. Because 2 minus bt equals 0, so this is what I did in my head. 2 is equal to bt, so t is equal to 2 over b. So it goes from positive to negative, but then there's an extra minus out here, so the p double prime actually goes from negative to positive. So p double prime is going to be less than 0 when t is less than 2 over b, and p double prime is going to be greater than 0 when t is greater than 2 over b. So we're talking about p is concave down, and then it's concave up. Now we can also, so basically we have concave down and then concave up. So if we're going to make okay, so we remember all of these results. If we're going to make a chart with all of this, okay, so this is at t is equal to 1 over b, and then t is equal to 2 over b. So we said that so what was happening with the derivative? The derivative was positive for t less than 1 over b, and then the derivative was negative after that. So p, I'm drawing the symbol for increasing and decreasing. So the derivative p prime was positive and then negative after this. Positive, positive. So that means that the function p is going to be increasing and then decreasing. Right? Because the derivative went from positive to negative. Now the second derivative went from negative to positive. And the transfer for the second derivative happened when t is equal to 2 over b, which is twice the time as the change in sign for p prime. So p prime changes sign at 1 over b, whereas p double prime changes sign at 2 over b. And p prime goes from positive to negative, p double prime goes from negative to positive. Well, if p double prime is negative, that means the function p has to be concave down. So this is going to be concave down, and then it changes to concave up. So there's an inflection point or a change of concavity exactly at t is equal to 2 over b. So to draw the function p, we need to basically just make sure that we preserve all of this behavior. So let me just select this stuff. Let's get rid of this. Okay, let's select this stuff again. Move it up here, and then get rid of all of this. Okay, so all right, so to draw the graph of p of t, so here we have the t-axis, and then we're going to graph p of t. Now, we'll note, so let me just rewrite p of t down here. P of t was a t e to the minus bt. We'll note that for positive values of t, p of t is always positive. So when we're looking at the positive time, p of t is positive. Also, p of 0 is equal to 0, because if I just plug in t is equal to 0, I get 0. We just get 0 goes in here and everything's 0. And then also the limit as t goes to infinity of p of t is equal to 0. So we know this because it's exponential decaying, and that wins out over any polynomial. So it's a function that starts at 0. It has a horizontal asymptote at y is equal to 0. So and it starts off increasing. It reaches a peak right here. So it reaches a peak when t is equal to 1 over b, and then it has a change in concavity at 2 over b. So first of all, it's concave down. So if we draw this, we get something that's concave down, increasing, and then it's concave down, decreasing. Then it changes concavity here, and it becomes concave up, which allows it to level off like that. So that's essentially what this family of functions is going to look like. So regardless of the parameters a and b, you're going to get some sort of behavior like this. Now, so we understand how the parameter b factors in, but what about the parameter a? Well, the parameter a basically controls the peak, right? So we have some sort of maximum value of p, and that's going to occur at time 1 over b. So p of 1 over b is a times 1 over b times e to the minus 1. So b itself controls at what time there will be a peak value of this function p of t, and then the parameter a controls how strong that peak is going to be. So the larger the value of a, the greater the jump. So you can create a very large jump and then have it decay off rapidly. So for a large value of b, 1 over b and 2 over b are going to be closer to the origin, and for a large value of a, you're going to get a very large jump. So for example, if you have a power surge, you might have a very large peak of voltage that then comes down in decay. So you get this large jump over a very short period of time. So that's why a function like this might be used to model something like a power surge.